Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 9th video lecture. And last time we ended the material for Chapter 1 of our text. So this begins Chapter 2 of our text, which starts off with the definition of a function and definitions associated to a function. So here's some, if you will, definitions. And so we consider two sets, A and B, and suppose that to each element x of A, there is associated an element of B. We're thinking only one element. Okay. Which we denote by f of x, then f is said to be a function of A into B. Sometimes we call it a mapping. So I'll put down here. Instead of function, we'll say, or, excuse me, mapping. Instead of function. Okay. That's the definition, what I just wrote, of a function, okay? And so here's another definition. The set A is called the domain of the function F. Okay, so that's another definition. And another definition is the elements f of x of B are called the values of F and then another definition is the set of all values of F is called the range of the function F. And we can look at a couple of examples. So here, we can have F, which will map from 0 to infinity. It's real numbers here, positive real numbers, not negative real numbers. Into R, and this is my A goes into B. So A is from 0 to infinity, subset of real numbers, into B, which is the real numbers, by, we'll define f of x equal to the square root of x. And we'll look at another example. So another example is we could define f going from, so my a here is going to be from minus 2 to 2 into r by f of x is equal to x squared. That can be a function. Okay, next thing we want to do is give a definition. And here it is. It says let A and B be two sets. And let F be a mapping function of A into B. Okay. Let E, or if E is a subset of A, f of E, so here's what we're defining, is equal to the set of all f of x's such that, f of x is going to be in B, such that x is an element of A. So that set is what we're defining. And it's called, then f of B is called the image of E under F. Under F. Okay? That allows us to get notation for the range of F, where A is the domain. In particular, what we have is f of A is the range of F Then we have a new definition. It says if f of A equals to B, then F maps A onto B. And the idea here is everything in B gets hit by something in A by F. So there's something for everything in B, for each guy in B, each element in B, there's something in A that F will grab its into. That's what it means to be, for F to be onto. Another definition is that if E is a subset of D, F raised to minus 1 of E is the inverse image of E under F and is given by F inverse, well, let me write it down here. F inverse of E, it consists of all the x's element of A, such that F of x is an element of E. So that's what the inverse image of E is. Okay. Another definition. If for each y in B, f inverse of y consists of at most one element, then f is said to be a one-to-one. No one writes down those words. We abbreviate that 1-1 function or mapping of A into B. Another way of thinking about this, or if x of 1 is different than x of 2, then f of x of 1 has to be different than f of x of 2. And f is one-to-one function. Okay, so what this is saying, he's saying, hey, look, if you got two different elements in the domain space, what they will be sent to are two different output values. And so that's what it means to be one-to-one. That is, to be one-to-one means there's no output value for function that is hit by more than one input value. Okay, here's another definition. It says if there exists a one-to-one mapping of A onto B, not into, more than that, onto B, we say A and B can be put into one-to-one correspondence. Okay. Or that A and B have the same cardinality. What we mean by that is that they have the same number of elements. The sets have the same number of elements. Okay, here I'll write this a little bit below. Or A and B are equivalent sets. Okay? Equivalent. Okay, and we denoted that by denoted by A tilde B, equivalent to B. Okay, well, there's another word or phrase that has equivalence in it. It's called equivalence relations. I want to talk about that. Definition. And equivalence relation, sometimes we denote it with this tilde, is a relation that satisfies three things. One is that x is related to x. Two, if x is related to y, then y is going to be related to x. And thirdly, if x is related to y and y is related to x, then, y is related to z, then x is going to be related to z. Okay, we're going to have a fact about sets being equivalent and that being an equivalence relation. Let me write that up. Yeah, so here's the fact. Equivalence between sets is an equivalence relation as 1, A is equivalent to A. 2, if the set A is equivalent to B, then B is equivalent to A. 3, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. We'd like to prove this. We'll get started here. I want to prove part 1. Well, here to prove that A is equivalent to A, means we've got to find a one-to-one and onto mapping, a function between A to A. And so I'm going to say, define f of A equal to A for all A element of A. We're going to show that that F is one-to-one and onto. Then F is onto A because for every A in A, there exists an A in A such that F of A equals to A. Okay. So what does it mean to be onto? For F to be go from A onto A means that in the image space, if you will, there for everything in here, there is something in the domain that's sent to it. And for everything in here, that's an A. What's sent to it is itself, A. That's onto. Then F is 1-to-1 as if A is an element of A, then the inverse image of that A, where A is in the range, okay, equals to A. So there's only one element. Now, the second thing, so this is proving the first thing. The second thing is we're going to let A be equivalent to B. We want to show that B is equivalent to A. Well, since A is equivalent to B, then there exists a 1-to-1 function, let's call it F, that maps A onto B. What we're trying to get is a function that is 1-to-1 maps B onto A. Okay. Now what we're going to do is we're going to define G, which takes elements of B into A, by G of B is equal to A if F of A equals to B. And the first thing to note is G is defined for every element little b in B as F is onto B. Okay. That is, for each B in big B, there exists an A sub B in A such that F of A sub B is equal to B. Thus, G of B is equal to A sub B. So G is defined for each little element, little b, element of B, big B. Okay. Okay, since F is 1-to-1, okay, then for each B element of B, there exists only one A sub B element of A such that G of B equals to AB. So that means that it is a function. The G is a function. Okay. So there was a question about maybe G grabbed an element from B and sent it to two different spots, but it doesn't. Okay. All right. Now, G maps B onto A as F going from A to B is a function. Okay, so what we mean by this is, so for each little a in A, F of A is in B. So G of F of A equals to A. Okay? So that's how we know that G is onto. Okay? You give me something in A, there was something sent to it by G. What was sent to it by G? Well, it was G grabbed F of A and sent it back to that little A. Now, G is a one-to-one function. Okay. From B to A, because that's what we're going to be looking at next. And because the reason is that we consider A an element of A, then the inverse image of A under G, let's see, that consists of all B's element of big B, such that G of B equals to A. Okay, so here's what we first observe. We know since G is, G maps B onto A, that G inverse of A is non-empty. Okay? So there was something that G grabbed and sent to A because G is onto. Okay? Now, here, if we suppose there exists a B1 and B2 elements of this inverse image of A under G, then F of A, okay, so what does this mean? This means G of B1 equals to A and G of B2 equals to A. That means F of A is equal to B1 and F of A equals to B2. And that's a contradiction. That contradicts F is a function. So F can only send A to one particular spot. Thus, what we have shown through this function G is that B is equivalent to A. I'll write that up. Because of the existence of the one-to-one function G that maps B onto A, B is equivalent to A. That was the second thing about the equivalence relations that we had to show. So the third thing is we're going to say, let A be equivalent to B and B be equivalent to C. We want to show that A is equivalent to C. That means we want to come up with some function that goes from A into C, where that function is one-to-one and maps A onto C. Okay. Well, here's where we start off. We say since A is equivalent to B, there exists F function that is a one-to-one mapping function of A onto B. Okay, similarly, we've got a statement that B is equivalent to C, so we're going to get another similar type function. That means there exists G, okay, that is a one-to-one mapping function of B onto C. Okay? So what we're going to consider, we're going to let H map A into B, into C, I should say, by H of A is equal to G of F of A. Then, what we're going to prove is, we will prove that H is a one-to-one mapping of A onto C. Okay. But before we go any further, let's note that, first of all, H is a function from A to C, okay, as for each A element of A, how are we going to find F of A? Well, we've got it defined here, but f of A is an element of C as f of A is equal to g of f of A. So here, F grabs A, sends it to something that's in B, G's going to grab that and send it to something that's in C. Okay? And here's what's written, where f of A is element of B and g of f of A is an element of C. Okay? And then, just as an observation, note H of A is one element in C as F is a function into into B, and G is a function from B to C. So here, the concern was, is there a chance that F grabs an element from big A and sends it to more than one thing? And the answer is no. And the reason is because F is, how is H defined? H defined of A is, first of all, F grabs A and sends it to something. So F is a function, it grab A, little a, and send it to only one thing in B, was called F of A. And then G is going to grab that F of A and send it to only one thing, because G is a function from B to C. Okay. And secondly, H is onto C. Okay? As, if you look at H of A is contained in C, we want it to be equal to C now. And so, and for every C in big C, okay, there exists a B sub C element of B such that G of B C is equal to this little c, as G is onto C. Similarly, for each B sub C element of B, there exists an A sub B sub C element of A such that F of A sub B sub C equals to B sub C as F maps A onto B. Okay. So we have that H of A sub B sub C, which equals to G of F of excuse me, A sub B sub C. Let me write down the right thing. Okay, and that's going to be equal to G of B sub C, which equals to C. So if you give me something in here, there's something in A. You give me some little c in big C. So this is a little c. There's some little a in big A that gets mapped to it by H. So that's why H is onto. And then the third thing that we'll claim here is that H is a one-to-one function So, in particular, if you look at H inverse of some little c, it's equal to the set of all a's in A such that H of A equals to C. And so, since H maps A onto C, this set is non-empty. That's a big C here, this is a little c. So since H maps A onto C, that means that H inverse of C, inverse image of this little c, is non-empty. Okay. Now, let's suppose there exists an A1 and A2 element of this H inverse of C, such that A1 is different than A2. We're going to get a contradiction here. So, H of A1 equals to C, and H of A2 equals to C. So this means that G of F of A1 equals to C, and G of F of A2 equals to C. Okay. But since G is 1 to 1, then that implies F of A1 must be equal to F of A2. Since F is 1 to 1, then A1 has to equal to A2, but that's a contradiction. So that is the proof. And we have shown that equivalence between sets is an equivalent relation. We'll talk about definitions of certain types of sets, classifications, if you will, certain classifications of sets. So here's a big definition. It says, for any positive integer n, okay, any positive integer, we're going to call it n, let j sub n be equal to the set that goes 1, 2, 3, all the way up to n. Then we're going to let j be equal to the set 1, 2, 3, 4, all forever. Be the set of counting numbers. These are natural numbers. Okay, so I call them natural numbers. And I usually denote that by script n, but our book denotes it by J. We'll use J. So we got a bunch of definitions coming. Then the set script A is 1. It's finite if A is equivalent to J sub n for some n or if A equals to the empty set or null set. That's one definition. Two, A is infinite if A is not finite. Three is countable, so A is countable if, sometimes we say, instead of countable, we say enumerable. If A is equivalent to the set of natural numbers, to J. 4 is uncountable if A is neither finite nor countable. And then fifthly, at most, is at most countable if A is finite or countable. Okay. Let's do one example and then call it quits for today. So as an example, kind of an example, or just a statement of fact, if you will. E equaling to the set 2, 4, 6, 8, 10, forever. These are the even natural numbers. Is a countable set. Okay, how do I show this? How do I prove this? Well, let's remember what it means to be countable. It means that the set is equivalent to the set of natural numbers, which we're denoting by J. So here, we want to show E is equivalent to J. And that's the same thing as showing J is equivalent to E. Okay? Well, here, we will show J is equivalent to E. That's right this way. Okay, and the way we do this, we consider F defined from J into E by F of n is equal to 2n. Then F is 1 to 1, and F is 1 to 1 and on to. So J is equivalent to E. I'm not going through the details of that. Just is. It's easy to see. Why is it 1 to 1? Well, if you say, give me something NE, what gets mapped to it? So something NE, let's call it little e, what gets mapped to it is E over 2. Okay? And then you say, so that's how it's onto. And then you say, how come it's a 1-to-1? Well, it's 1-to-1 because for each thing in here, there's only one thing getting mapped to it. That's this N. So we'll end it with that. That's the description of the details. And that'll be enough for today. Thank you very much for your time and patience.